Hi, this is Dan Bullard, retired electronics engineer, sitting on the front deck of my output again. So this is the last module of the Nextest DSP training course, and this is on ADC testing. With ADCs, we do not put in a ramp and look for a deterministic vector. So we don't put in 0 and look for low, 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 and then put in a 1 and look for low, 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 high, and so on. We don't do that. That's not the way ADCs are tested. They're analog components. They're analog devices. Hence the name. ADCs cannot be tested using deterministic vectors. An ADC is not a digital part. It's an analog part. It does put out digital at the end, but it converts analog to digital. So we have to treat it like an analog part. ADCs are often tested more like a comparator. Since a typical ADC is based on one or more comparators, it makes sense to test it that way. I've tested quite a few ADCs, analog digital converters, quite a few of them. You're probably using some of them now. And I don't test individual components. I write test programs to test millions of devices, millions. And my code is out there in the world right now running. I'm nowhere near it. They don't even know who I am anymore. Here's the kind of thing that we're going to do. We're going to take a comparator. We're going to treat it like a comparator. We're going to run a ramp past the positive input with a VREF on the negative input and look for the output to flip from a low to a high. That's how we're going to test it. Here's a little 2-bit ADC, just a little example of what it might look like. So we have plus VREF and minus VREF, and they're going through a resistor ladder, and we take the input to all the comparators. The voltage in is compared to those voltages off the resistors. The output goes into an encoder, and then it gives us 2 bits or 4 bits or 16 bits or 24 bits or whatever. ADC testing duplicates comparator testing to 2 to the nth degree. Drive a ramp in with 2 to the n times 10 levels. It requires 3 to 4 more bits than the DUT. Capture the output with the ECR. It was called the error capture RAM back when the Nextest was just digital, which we renamed to be the digital capture instrument for the mixed signal. And Daver worked his magic on it and made it more like a digital capture instrument. Most mixed signal testers have a way to capture digital data that represents an analog waveform. Ensure all comparators did trip. That is, you have no missing codes. That's kind of an important thing. Here's an example of how we're going to do it. We're going to use the arbitrary waveform generator to generate a waveform. The arbitrary waveform generator is called AWI, arbitrary waveform instrument. With the Nextest, we're trying to differentiate ourselves from everybody else. So ACI, AWI, DCI. What we have here is we have the clock generator, which is coherent with the digital. So it doesn't have to be at the same frequency. It doesn't have to be synchronous with the digital, but it has to be coherent. We have the clock generator going to an address counter and a 256K waveform memory. The memory goes to a 14-bit DAC, and that was the AWI, and that generates an analog waveform. So we load our waveform, and it's going to be a ramp this time. Load our waveform into the AWI memory. We generate the clock the data into the DAC, and the waveform will come out, go into the DUT, device under test, and the DUT will digitize it. And we're clocking the DUT with digital pins usually. So we clock the DUT, the ADC, with digital pins. We get digital data out. That goes into the DCI, digital capture instrument, also known as the error catch RAM. Here's how we set up the ramp. We're going to put a ramp into the AWI and generate that, clock it out to the part. We're going to do 2,816 steps. That's 10 times 256. So this is like an 8-bit ADC. 10 times 256 plus 10% overdrive. And you're saying, why are we doing overdrive? This is not like the Hot Rod Lincoln. We don't need overdrive. Well, we do. We need to overdrive. We're going to take the input from below minus VREF all the way through its range and above the positive VREF. So we take it from minus VREF to plus VREF with 5% overdrive on the low side and 5% overdrive on the high side. We take 22,528 samples, which is 2816 times 8. So we don't have to put them all in memory. We simply tell the AWI to run over and over and over and over again. And now we're going to do a histogram. How does the histogram work? We read each value in the AC/DC output ramp. Every time a particular code is encountered, increment the bin associated with that code, i.e. generate a hit. It's a bin histogram, just like a spectrum is a bin histogram. The histogram will contain 2 to the n bins. We hope that every bin will contain the same number of hits, except the first and last bins. They'll contain the hits and the overdrive codes. So here is our histogram, and I think this is a real histogram from a real ADC. We get 80 hits per code. There's the 80, right? And you see it bouncing around a little bit. Sometimes, I mean, we're talking about tripping comparators, and there may be some noise on the signal. Now, this is an 8-bit part. You think about a 16 or 24-bit ADC, it's going to have a lot of noise popping up, so it's going to be a little noisier than this. The average is 80 hits per code. 256 times 10 times 8 divided by 256. Do the math. Okay, at the very ends of the histogram, at the bottom end and at the top end, we see the overdrive. So that's where the waveform was presented to the ADC, but it did not yet have a value high enough to be above the minus VREF, or at the other end, low enough to be below plus VREF. Here's an INL failure. And you can tell because we see a tilted distribution. Okay, so that's an INL failure of the ADC. We can measure that directly with Davers functions. And here is a DNL failure, okay, and this is right in the middle of the ADC's range. And so here we got 128. We didn't get any codes at 128, but we got the extra codes that belonged in 128 in bin 127. So there's a bad bit there. So we have a DNL failure. We see that with ADCs differently than we see them with DAC. Okay, let's talk about generating histogram. Waveform histogram, waveform out wave, waveform in wave, double low bound, double high bound, and number of buckets. So in this case is 256. So it depends on the number of buckets for your device. Remember, it's a bin histogram. And I've used these before. Early on, when I was at Genrad, I'd never heard of a histogram, didn't know what a histogram was. I mean, I was kind of green. And I was working on a random number generator it was something I read in a book. And I wanted to find out if the random number generator was really random. And so I invented a histogram. So I made a histogram based on something that I was fooling around with VT100. I got really good writing code for the VT100. I wrote a program that made it snow on the VT100, which is not easy to do because on a VT100, it's meant to only take text up, and I made it send text down. So it's pretty cool. So I converted that. So not everything I did was a complete waste of time. Lots of things were. But here I made a histogram to capture the distribution of the random number generator. So I let the random number generator run over the weekend, and it generated a histogram and captured the distribution of the random numbers. So as the random numbers were generated, it filled up the histogram, and I found out that yes, it was truly random. Well, pseudo-random, because if you start with the same seed, you get exactly the same numbers. But what's important with a random number generator is the distribution. not the individual numbers. If you want a really random number, seed it with something. And that's what we did in crypto. Okay, analyzing the histogram. To analyze the histogram, we generated already, we use Daver's functions. He wrote a couple of functions. Waveform, ADC, ramp, INL, DNL. You give it the waveform, and you get two waveforms out. You get out INL and out DNL. You get two doubles, the integral linearity error and the differential linearity error. And then you give it variables to get the ILE index and the DLE index. And then, same as the DAC, you give it the line fit method, and the default is T-adjusted fit. Waveform, ADC, ramp, INL, DNL. You give it the waveform, and you get basically just two outputs, the ILE and the DLE, and you can look for the index if you want. So Daver was pretty good about this. Some people think that it's not legitimate to use ramp to test linearity. They want to see it done with a sine wave. And so that's a bit of a problem here, isn't it? Because a sine wave does not have a nice flat histogram, okay? But some people believe that a sine wave is the only way to test these things. Now, you could do a sine wave and do THD, but that's going to kind of look on poorly. So that's not really, and you can do an intermodulation distortion. That's another way to do it. But so, I mean, every company has their own strategy for this. For example, at Maxim, for their audio devices, they didn't limit themselves to like 3 or 4 harmonics for THD testing. They went ahead and tested it at 1 kilohertz and tested 20 harmonics, because that's what the human ear can hear, is all the way up to 20 kilohertz. So that was their rule. Every company has their own rules for these things. So in some companies, they want a sine wave histogram. So we set up sine wave linearity. Sourcing a sine wave into an ADC results in a bathtub-shaped histogram. Sine wave linearity functions must be used instead of the ramp functions. Here's what a histogram looks like for a sine wave with the bathtub. It looks like a bathtub. Some people insist on this, and you can't say no. I mean, the customer is always right? We had 2 functions for it. Waveform, ADC, sine, INL, DNL. You give it the in wave, and you get the 2 output waves, the INL waveform and the DNL waveform. Waveform, ADC, sine, INL, DNL. You give it the in wave, and you get 2 variables out, DNL and INL. That's ADC testing. So anyway, that's the end of the Nextest DSP training class. I only presented that to you because my boss, Rick Carmichael, has died, and he won't object to it. I don't think anybody else will either. They don't teach this stuff the way I teach it, okay? I don't know what they're doing these days, but I'm the guy who wrote it. So that's my class. I wrote it. So once again, from the river, this is Dan Bullard. See ya.